this is the last part of our lab 8, which is also our last lab for our Introduction to Fluid Mechanics ENGR 3404. So in our last part of the lab 8B, we're going to study the energy losses in bends, which is also a minor head loss. So let's see what is our learning objective for today. So we're going to investigate the head loss in fittings. So for example, in this equipment, you have long bends, enlargement, contraction, small bends, and then you have miter bend, and you have gate valve. So this kind of fittings can cause head loss, and these are the minor head loss. So we're going to investigate the minor head loss in those fittings. Now, through that, we're going to determine the head loss coefficient for minor head loss. And finally, we're going to investigate the relationship between head loss coefficient, which is K, and the volumetric flow rate, Q. And again, head loss and flow rate, which is V, velocity. So, let's take a brief moment to cover the theory. The head loss in pipe fittings are defined is that del H, so it's in meter. K is your head loss coefficient, which will be different for every different types of fittings, and velocity is the flow of entire pipe. So we can always find the velocity if we can collect the water flow at the end over a certain period of time, and then if we know the cross-sectional area. So again, just a quick recap of how do we measure the head loss del H in our system. If you remember, on our lab 8A, our pipe was smooth and the diameter was fixed. And now in this case, in the pipe fittings, there will be contraction and enlargement. So there is change in diameter. That means there will be change in velocity. And that's why the equation will be a little bit different from section to section. So again, if we apply the Bernoulli's equation, for example, in this case, if you see here, this is the inlet of the long bend and this is the outlet. Here, the diameter of the pipe doesn't change. If it doesn't change, we still stick with the same concept. Del H would be only the change in pressure. This doesn't exist because there is no change in velocity within this length of the pipe because there is no change in diameter. So this will not exist for when there is no change in diameter. So for a calculation of this one, we can just get the pressure head if we know the head loss, if we know the pressure difference using the manometer. Now for a section like this, if you see here, this is the original diameter of the pipe and this is thicker, so there is an enlargement. And if there is an enlargement, there will be change in velocity. So only change we'll have, then we cannot say the V1 equals to V2, we cannot say that. And if we neglect the elevation, we can write the del H should be the pressure difference, also the kinematic pressure difference. And how can we find the V1 and V2? So again, for the contraction and enlargement, we have to, after we take the manometer reading, we have to balance doing this, adding with the pressure difference that we find. And to find this, we need to know the velocity. How do we find that? If we collect the total water flow, and if we know the cross section of this contraction and enlargement cross section, we can find those velocity. So by contraction, what I mean is that from contraction, you're gonna go to enlargement. So a small diameter, you are at contraction, so you are at minimum diameter, and you're going to the enlargement. In that case, your velocity will be higher in this region, and velocity will be lower at the enlargement region. On the other hand, when you are in the enlargement section and you're going to the contraction section here, your velocity will be whatever velocity you have, the velocity at the contraction region will be smaller. So let's move forward. Okay, so Reynolds number. Again, for this type of flow, we also can find the Reynolds number using the same theory that we have covered for the lab 8A. We know the water density. If we take the water temperature, we can find this mu, and then kinematic viscosity, we can also find it. If we just know this one, we can find this one easily. And diameter is given for the pipes, and velocity we can collect the water and divide it by the cross-sectional area, so we can find the Reynolds number. So the Reynolds number for this lab will be used to determine whether your flow was turbulent or laminar. So let us introduce ourselves with our equipment. So this is the setup for our minor head loss due to flow through pipe fittings. So what we have here is that we have a pipe system. It has a lot of fittings here. We have a long bend here. From here, you see, from here to there's a thickness change. So this is the area enlargement, and from here, if you see from here to here is a diameter change. It gets smaller, so there is area contraction, and we have a small bend. We have an elbow bend here. We have a gate valve, and we have a miter bend here. So what we're trying to do is that we're trying to measure what is the head loss when the water flows through these fittings, these bends. So how it is connected is that, if we want to measure, for example, what is the head loss when there is an area enlargement. So from here to there's a change in diameter, so area enlargement. What is the head loss over there? So what you have to do, you have to take the pressure at the low diameter or actual diameter. So that is this diameter pressure. This pipe is going to reading that pressure, and then there will be another pipe that is coming out after the enlargement. So if we can connect these two, so this is the enlargement reading on the manometer. So one is connected after the enlargement, and the other one here is connected before the enlargement. So this is how we're going to measure the differences in the manometer, and this is how we're going to measure the head loss for each fittings. Same for example, this elbow, this small bend, we will have one outlet after the elbow and then one would be before, and if we can differentiate between two pipes, 2 manometers, and we can measure the head loss. For the gate valve itself, we have the gauge here, or we're going to use this gauge reading. So this is the top part of the manometer here. We have one here is air bleed screw. What it does is that if you open it, it lets the air into the manometer, and then water will fall down. So we'll keep it closed. And here we have air connector. What I'm doing is that I'm opening the air connector. So there is a cap on the screw. So I opened it, and I'm connecting a hand pump over there. This will be needed if the water is too high, and then I cannot take any reading. So if I need to lower the water head, I can push some air into the top part of the manometer, and the water will come down, and I can take the reading. So I'm connecting the hand pump. You see, it will let some air in. See, the water level is going down if I pump. So if we need it, we'll do it, but for now I'll just close it. All my manometer inlets and outlets are open. All of these valves are open. Now I can turn on the pump to take our test data. So for this test, we're going to do the data collection in two stages. First, we'll keep this valve fully open and we'll measure the manometer reading for each of those. I'm going to show you in a little bit. We have names, which manometer is going to give us which reading. You can also look at the pipes and also know where it is coming from. So that will be the first stage. On the second stage, we will not gonna use this manometer. We'll close the manometer outlets and we'll use this gauge reading for the gate valve friction gate valve minor head loss. So first part we're going to use the entire feedings except this one, and then for the second time we're going to just use this one. So the data collection. Data collection for the minor head loss in pipe feedings. We have to know the diameter of the entire system was 0.018 meter. Only where there is enlargement, that diameter is 0.024 meter. We can take the water temperature, and what we have to do is that for all those changes, there's a contraction, there's enlargement in the system, short bend, long bend, elbow, and miter. We have to take the manometer reading, H1 and H2. This will be H2. Then you can measure the head loss by taking the difference. You have to collect the volume of water over a certain period of time. That will give you the flow rate, and from the flow rate with the cross-sectional area you can find the velocity, and you can find the kinematic head, and from the theoretical equation that we just discussed you can find your coefficient of head loss for each of those feedings. There will be different K, and then you can also find the Reynolds number, whether the flow was laminar or turbulent throughout the system or different, and where the change or their change in Reynolds number on those feedings. So I have turned on the pump. There is no water flow. I am slowly opening the pump. Slowly. You see the manometer reading is going up. All the manometer is being filled with water. So the pump is running. There is no air bubble into our manometer. It is totally filled with water. Now we have to lower or control the bench valve from the pump so that the water flow rate into the pipe is no more than 17 liters per minute. We have to do that because if we have more water flow, the pressure will be high and we will not be able to take reading using this manometer. So we have to keep the water flow up to a certain limit so that we can take the reading. Now it is totally full, so we cannot take the reading. So we have to lower the flow rate below or at 17 liters per minute. So how do we do that? We're going to keep reducing the flow rate through the bench valve gate, and we're going to measure the water collection over there, and from there, given in time, what is the volume of the water? If we can divide that, we can collect what is the flow rate, and from there we can measure whether it is below 17 or not. So I'm going to lock this outflow. Now water is going to go high up on this meter in your bench valve here. So on this reading, I'm going to use this reading using a time. So I'm going to measure how much water filled up given a time, and I can measure the flow rate. So the pump is running, the water is going up. My goal is to have no more than 70 liters per minute. So what I'm going to do is that when I have a mark, for example now it's 2 liters, I'm going to start
and what I'm going to take is that how much time it takes to fill 5 liters. So it was here 1, 2, 3. So how much it will take to be at 7 liters. If I can get 7 liters in 20 minutes, then I will have about 15 liters per minute. So I will be well below the range of 17. So I'll be good to go. So I'm only 22 seconds and I'm about 17, so I'm good to go. So once I know that my flow rate is below 17 liters per minute, now the data collection is very easy. For this case, you see the water level on the manometers are below within the range, and if it's not, if it's the water level is way up, you can open the air bleed valve to get some air in. If it doesn't work, then you can pump some air, but in this case I don't have to because they are well below the limit. So now you see it has the tag enlargement, contract, long, that means long elbow here, short elbow, elbow here, and minor elbow over here. The valve is fully open. So all I have to take is the reading, take the reading between these two. So you see, if you take the reading between these two, sometimes you will see the water level is dropping. What you can do is take a picture of an instant and take the differences. So all you have to collect is the head difference, maybe H1 and H2, and take the difference at any instant. And then you will take the data for all those losses. Next, what you have to do is just change the flow. Maybe lower a little bit, maybe up to 10 liters per minute or 12 liters per minute. Take a different flow rate between 8 to 17. It has to be between that flow rate, and take data point, take the minor head losses.
So the second part of the data collection, so there's two types of data collection. If you remember our setup, there was a gate valve. We'll just keep the gate valve wide open for the first set. For the second set, we're gonna just deal with the gate valve. So this is the data collection for minor head loss across the gate valve. So in the gate valve, the reading will be given in bar. So we can target a head loss at, for example, 0.2 bar or 0.3 bar, 0.5, 1 bar. And you can convert equivalent bar to, so it will be using calculator, you have to convert the equivalent bar to meter head loss. And again, similarly, you can collect water, use time, and find the flow rate and velocity, and get the kinematic head and K and Reynolds number. So let us see how the test procedure for data collection.
So the second stage data collection is only for the gate valve. I keep the gate valve fully open, and I also open the bench valve fully open, so the water flow is very high. We are neglecting this manometer, we're not using this anymore. We're going to use this gauge reading over here. So now it is fully open, and you see there is no reading here. What we have to do is that we have to close those reading. We have closed this valve to get some reading. So our target could be point. These are in bar, so we have to take the data in bar and then later convert it into meter water head. So I'm keep closing the valve so that I can get a fixed reading over here. So for example, 1.1. So maybe 0.2. So at this position, the valve is closed and I have a reading of 0.2. Now what I can do is that again close this valve here and record the water volume given a certain time, so we can know the flow rate, and the head loss would be 0.2. Again, you have to repeat the data, closing further. So now I'm about 0.4 now. So again, at this position, you have to take the reading, how much water volume is collected given a certain time, and this is how we're gonna collect the data for the gate valve minor head loss. So I'm gonna show you a close look of that. So this is the close reading. It's in bar for the gate valve. You see the gate valve is connected with that gauge reading. And at this position, I have about 0.4 bar. And what I have to do is that lock this knob here so that I can collect the water flow and measure the time, how much, and then measure the water flow velocity and flow rate. If you see closely, the yellow tubes, one is connected above the gate valve, one is connected below the gate valve, and both of them are fitted into the gauge reading. So whatever the difference we'll see here, it is the head loss at the gate valve. This is the back side of our system here to show you our long bend. You see here, this is our long bend, this one. And so that is on the back, that is our miter bend, and this is the test rig flow control valve. I also have to take the reading for water temperature, so I have a thermometer here. What I'm going to use that over here in the tank and put it inside the water, under the water, and I can take the water temperature reading this way.
So we have finished our data collection. In discussion, we have to plot the head loss for both tests with dynamic head. So remember, for the second data collection, which was across the gate valve, your head loss will be in bar, but you have to convert it into equivalent into meter. Then you have to plot the K, the coefficient for each of those, and with respect to Q. And you have to discuss whether the trend line you see, whether they're expected or not. And then you have to examine the Reynolds number that you have calculated for all those fittings and the gate valves, and comment whether the flow was turbulent or laminar, whether they were turbulent all over all those fittings or they changed a little bit or not. And finally, you have to comment if we can assume a constant head loss coefficient for entire system or should not be. So that was it for all 8 labs. We have studied 10 equipments over the 8 labs. So lab 8 and lab 4 had 2 equipments. So total 10 equipments. And so that concludes our labs for this course, Introduction to Fluid Mechanics lab part. Thanks for watching. If you have any question, you can always comment. We'll see you in next video. Thank you.